Now that we've gone over how phasors behave in transmission lines, we're going to take a look at how to calculate the power or convert that voltage into power, which is usually the unit that we're often talking about. So to start out, let's just recall that the phasor form for the voltage for a wave that's propagating in the positive z direction will be some amplitude. If it's lossy, it's going to decay by e to the minus alpha z, and e to the minus j beta z. Now the current, in the case of a positive z direction, we just simply take this and divide by z naught. And remember that if we're talking about a wave propagating the positive z direction, don't forget to add the negative sign. And the main formula to remember is that the time average power is going to be, where this bracket is referring to the time average, is going to be equal to 1/2 the real part of Vs times Is conjugate. So remember, the conjugate means that this beta term goes away, so you're left with everything that's V naught e to the minus alpha z. If we plug in our phasor form for Vs and Is, we can then rewrite this in the following form here. So 1/2 magnitude V naught squared all over the magnitude of z naught. Remember, z naught is a complex quantity, and so here we're going to take the magnitude, and to account for phase mismatches between the voltage and the current, we're going to add this extra cosine of theta term, where theta is the current phase shift relative to the voltage. So as you can see, if the impedance is a real quantity, then the two phasors, the voltage and the current, will be in phase. And so you're just going to get straight up these two multiplied together, which is what you see here. But if they're out of phase, you're going to have this extra theta, and that theta will reduce this overall power. So if you can visualize it, let's just say the voltage in this case, let's just say it looks like this. And in the case of if the current is in phase, then any point when you multiply them together, you're going to get just the product of the two. But if, on the other hand, if there is a phase difference, then if you have the voltage here and the current is just a little bit out of phase by some angle theta, you'll see that when you take 2 points and multiply them together at any point in time, you're going to get less than the product of the two. So that's where this cosine of theta comes in. The other concept that I want to get across is you want to be able to describe the power loss in units of decibels. So one thing to note is that you might hear about decibels, and some of you might remember the unit dBm. And remember, decibels is a relative quantity. So what I like to think about is, if we're thinking of power in terms of elevation or altitude, I like to think of this in terms of if dBm is meters, it's relative to sea level, and then dB would just be meters. So it wouldn't have, so dB by itself is just comparing two quantities, and you say, oh, the altitude, between the airplane and the person is this many meters. But it doesn't really tell you where they are specifically. dBm is an actual power quantity because you're comparing it with 1 milliwatt. Or so equivalent would be, you have this airplane and you're comparing it with sea level. So make sure to keep that in mind. In this case, we're talking dB, so we're just comparing two quantities, and namely between the input and the point of interest. So the formula for that is 10 log, this is log base 10, of time average power at one location versus the time average power of your other location of interest. And note that since there's a v naught, since the power is proportional to v naught squared, if you put that in, then you also can use the rule that log of a to the n is going to be equal to n log of a. And so you can also see that this is going to be equal to 20 log base 10 of v naught of the voltage at those two locations, so voltage of A versus voltage of B. So the thing to keep in mind is that the power, if you are looking at it in terms of voltage, don't forget that you have to multiply it by 20 instead of 10. And kind of along those lines, you can see that since you're multiplying these two together, your power, while your voltage decays as a factor of e to the minus alpha z, your power, your time average power in this case, decays with e to the minus 2 alpha z, and that's because it's the product of these two. The last thing for this topic that I want to leave you with is a useful rule of thumb that since, say, your power level at a location, if you're comparing it to z equals 0, would be power level at z equals 0 and then this e to the minus 2 alpha z decay. The power loss, we can do a little bit of simplification, which is you can take power of a particular location compared to the power at z equals to 0. And we know what the relationship between these two are. So you can write this as log p of 0, p of 0, and these cancel out. But as it propagates, it decays by e to the minus 2 alpha z. You can then rewrite this e to the minus 2 alpha z as 10 log of e to the minus 2 taken to the alpha z, which according to this rule here, we can take out this alpha z, so you're left with 10 log of e to the minus 2, and then this whole thing times alpha z. And these are all known quantities. And so by plugging that in, you can find that the power loss when compared to z equals 0 is probably going to be about equal to 8.69, which is what this value is, alpha z. So this is a nice way to roughly estimate what the power loss is if you know what alpha is as a function of location. And it can be a general rule of thumb to estimate how your signal is going to decay in units of power, in units of relative power as you propagate down while using a cheaper calculator.